This tutorial explains how to decouple the physics from the rendering in order to interpolate or extrapolate changes in position and rotation. For example, if your monitor's VSync refresh rate is 120 frames per second and VSync is enabled, but your game's physics only runs at 60 frames per second, then interpolation, which is also known as in-betweening, allows you to render position and rotation values that lie in between the last two known physics frames. For 120 frames per second and 60 frames per second, there would be two rendered position and rotation values per physics frame, thereby taking full advantage of the monitor's high refresh rate to produce extra smooth animation. Linear interpolated values are calculated proportionally, such that the amount of time passed since the last completed physics cycle as a percentage of the physics frames per second time is then multiplied by the physics step amount, the result of which is added to the last but one known physics value. Because interpolating involves calculating in between two known values, it results in the rendered values lagging behind the most recent known physics values, anywhere from 0 up to one complete physics frame, but it has the advantage of never producing values that lie beyond the most recently calculated physics state, unlike when using extrapolation. In contrast to interpolation, extrapolation is almost the same thing, apart from that the percentage of time passed since the last completed physics cycle is instead multiplied by the most recently calculated physics values, instead of by the last but one known values. However, in either case, whether interpolating or extrapolating, rendered positions are either going to lie before or beyond the most recently calculated physics values, although that discrepancy can be extremely small. Another very important advantage in addition to having butter-smooth graphics is that everyone will have a consistent gameplay experience regardless of their monitor's settings, because the physics routines are now operating as being decoupled from the rendering routines. To calculate in-betweening values for the rendering draw calls, you can either use one or two threads, but I prefer to use just one thread for reasons which I'll demonstrate shortly. Multi-threading for various other aspects of a game can obviously have its advantages, which apart from the frame-by-frame interpolation and extrapolation, might well include various other aspects of the physics routines. To help concentrate on the programming aspects that are specifically related to interpolation and extrapolation, I've decided to revert back to Tutorial 5 Model Loading Part 1, and therefore adapt and develop this tutorial moving on from there. Let's start by taking a quick look at the main.cpp file, and then continue by examining the code for the one thread option, and also run the program to demonstrate both interpolation and extrapolation. There are 5 new includes, which are the C++ thread, atomic and mutex includes, and then also our 2-thread classes, which each receive references to the window object and the shaders. The only other difference is that the model being rendered is now declared and initialized within each thread class, but everything else remains the same as in Tutorial 5. To run the one thread option, you just need to comment these 4 lines, this line and these 2 lines, and uncomment this line and this line, and then recompile the program. I've added a timer for the purpose of being able to simulate the main loop frames per second as being either faster or slower than the monitor's refresh rate, which to work correctly requires that VSync is disabled, which can be done by setting the GLFW swap interval to 0. By making the main loop in the main thread wait for the monitor's VSync signal, it rests both the CPU and the graphics card because the main thread is being blocked from running. Let's start by disabling the rotation transformation by setting animate to 1 in the vertex shader, so that we can concentrate solely on how the position values are extrapolated. Before we start examining the code, let's first watch the program running with the physics frames per second set to a very low value, and when discarding the extrapolated values, which as you can see looks very lumpy, which corresponds to the values displayed in the console window. If we then add the current extrapolated render value to the current physics position, the motion becomes butter smooth. The section of code responsible for producing the extrapolated time percentage value is just this small section here. The first line calculates the total number of physics cycles that are due to run, which typically varies from 0 to several physics cycles per VSync cycle. The current target time value is never greater than the total elapsed time value, because the current target time value is only ever increased by some multiple of the physics frames per second time, which the total elapsed time must have already exceeded in order for the current target time to be increased in the first place. Likewise, the overlap point in time is also set as that same multiple of physics cycles time, but by adding it to the previous current target time. The extrapolated percentage in the range 0 to 1 is the overlap time divided by the physics frames per second time, which is the fractional value used for rendering the position. The drawObject function multiplies the interpolated or extrapolated value by the object's translation step value, and then adds that result to the object's current position. When running the program using this 60Hz monitor, and with the physics rate now having been set to 80 frames per second, then 1 in every 3 times that this subtraction is greater than or equal to the physics frames per second time, the physics routine is called twice. As you can see in the console window, every third execution of the if statement results in 2 physics cycles. Now let's set the physics ridiculously high to 600 frames per second. We're now getting a consistent 10 physics cycles per VSync cycle. Let's now reduce the physics rate to 10 frames per second as before, but this time we'll examine translating the position in a little more detail. Within the process physics function, we simply increase the object's position by the translation step value, but look what happens if we increase it after the potential change in direction instead of before. When the direction changes, the rendering skips a position, which is because the physics is no longer being allowed to catch up with the rendering, and therefore the result is this skipping type visual artifact. Notice the rendered position values displayed in the console window as the direction changes. I've set the physics step value to 1, which results in a rendered position skip artifact of 1, in contrast to the otherwise much more gradual change in rendered position. By allowing the physics to catch up to eliminate the skipping, it only works because the physics step is in the same direction as the extrapolation, whereas the more significant the change in direction is, the more noticeable this visual artifact would be. Now let's enable only the rotational aspect of the animation within the vertex shader. Notice that the rendered rotational position values are currently set as being interpolated instead of extrapolated. If we now discard the interpolated values, then just like when translating the position, the animation becomes very lumpy. If we now extrapolate the rotational position instead of interpolating it, then we get the same skipping artifact as demonstrated for extrapolating the position, which is because unlike for the position, the change in direction, being rotational direction this time, is random. Because interpolating involves selecting a value between 2 already known values, notice that I've made a copy of the physics rotation matrix immediately before updating it, which is then used as the previous known value. If we now disable VSync and use the timer instead, and set the timer to a ridiculously high value such as 1000 to simulate the interpolated or extrapolated values of a ridiculously high monitor VSync rate, we can see that for a minuscule physics rate of just 1 frame per second, it produces 1000 interpolated or extrapolated values per physics cycle. Finally, let's take a quick look at how to produce these in-betweening values when using 2 threads, instead of just the main rendering thread. The first thing is to enable the 2-thread option in the main function by commenting this line, and uncommenting these 4 lines, this line and these 2 lines, and recompiling the program. The timer, VSync setting and physics values are all set the same as when using the single thread option. All the values being accessed in both threads have been placed between the mutex locks, which stops race conditions such as reading from variables and writing to them at the same time. The physics routine runs on the second thread, which is controlled by a timer. I'll demonstrate the thread precision time scaling shortly, but for now I'll explain about the thread last time variable, which records the time that this mutex physics block last executed, which is then read in the main rendering thread and used to calculate the delta physics time. The interpolated or extrapolated time is the delta physics time divided by the physics frames per second time. That value is then multiplied by the physics step amount, the result of which is added to the object's position, which then gives us the rendering position value. Similarly, the interpolated or extrapolated values are also applied to the rotation matrix. The drawObject function simply sends the transformation matrices to the vertex shader before drawing the model. To finish off, let's now examine the purpose of the thread precision time scaling variable. I discovered that the timing of the thread, although always consistent, can be significantly off target if the physics rate is set to a ridiculously low value. I've decided to demonstrate the stuttering effect that occurs by setting the physics rate to a minuscule 2 frames per second, but from testing 10 frames per second and above, I found it still looks butter smooth. You can see that the stuttering is clearly visible, and also notice the thread cycle time, which is set to be exactly 0.5 seconds, but is taking roughly 5% longer. If I now enable the thread precision time scaling, we're back to having butter smooth extrapolation. Finally, let's look at how the mutex locks affect the synchronization of the two threads. When the mutex locks are enabled, if we then enable these two for loops which each display a numbered sequence of characters, each row displays in turn as would be expected when using just a single thread. However, if we disable the mutex locks, then periodically both for loops execute at the same time, which results in the numbered sequences becoming intermingled. That's all for this tutorial, so if you found it interesting, please click on the like button and you can always subscribe to my channel. Thank you.